So, in our first hour, we talked about the most important phrase you could come away from this day with knowing, which is, how do you know that? Never, ever, ever be afraid as Christians to ask that sentence. Because honestly, I feel like we are getting to the point where nobody else is going to do it. This might be the single best thing as Christians we can do in our vocations outside of the church walls other than sharing the gospel of Jesus Christ with people. Which is when somebody comes up with some statement to say, and how do you know that? And to get people thinking about how they know the things they know. Right now, what we're going to talk about for the next hour is some of the things that we actually do know for certain from what we are going to call observational science. Science that is about the here and now and using the scientific method to discover things. And what that says about Romans chapter 1. We've had the veil lifted from our eyes. We know that we are seeing in creation signs of God's invisible attributes. And we're going to look at some of the things that we actually do know and what they say about God. We're also later going to talk about, in probably our last hour, places where we do get into trouble, where then we take the word science and make it more broad than the scientific method. This is where we get into age of the universe, we get into the Big Bang Theory, we get into evolution. But I like to leave that last, because to me it's much more fun to talk about the good science and where that points when it comes to us as Christians. One of the places I like to start is with general relativity. And if I could, I'd like to step back for a moment and just remind us of what it was that relativity did to our understanding of how the big universe works. So now we're thinking telescopes, we're thinking space, we're thinking large distances, long periods of time. Back a number of hundred years ago, we had this wonderful Anglican by the name of Isaac Newton, who discovered the way that God normally runs the universe on our scale, on a human scale, on things that are on the scale of a church building or a human being or animals that we can observe easily with our own eyes and touch with our own hands. And he discovered that very, very simple, if I might even say elegant and beautiful equations govern the laws of motion and force between different bodies. Very, very simple laws with very, very simple constants. And he was the one, of course, who figured out that gravity has an influence on every body in the universe. So there is actually a force of gravity between us. It's a force of gravity between the building and us, force of gravity between the planet and us. And it's a very simple equation that determines that force. This is the idea that a body that is not in motion tends to stay at rest. But if you apply a force to it, that body wants to stay at motion unless a force is applied to it to stop it. So for a number of years, Isaac Newton's view of the universe prevailed. And even though Newton was a fairly devout Christian, those laws actually led to a view of the universe that was kind of un-Christian. He actually laid the foundation for what we call deism. Deism is the idea that yes, there's probably a God who in the very beginning gave the first push that set everything in motion, and after that, he's basically been on permanent sabbatical. So God is at rest and just watching the universe operate like clockwork, because Newton's laws look like the whole universe just does work on clockwork. And a fundamental part of Newton's understanding of the world was the idea that time is a kind of permanent, unchanging constant. Time flows the same for all people, everywhere, and doesn't change. Time like an ever-flowing stream, right, as the hymn says. Then Einstein came along and completely changed our understanding of the nature of time. First thing he did, of course, was discover the principle or discover the relationship between matter and energy, which were sort of thought of as being two distinct things. But Einstein discovered that really they're two sides of the same coin. And they are also related by an incredibly elegant equation. Energy is equal to mass times the speed of light in a vacuum squared. Or, as you all come to know it, E equals mc squared. Like Newton's laws, incredibly elegant. Now, this in and of itself is starting to show us something about the way God operates the universe, which is that the ways that he does it are incredibly simple, and physicists actually use the word elegant and beautiful when they describe equations. In fact, it is now a principle for testing theoretical physics theories. Do the equations look nice? Are the equations elegant? Now, what's the question that we're all learning? How do you know that equations should look elegant or should look beautiful? Why should that be the case? And when you ask that question to physicists, they get very nervous. And they look at their shoes, and they sort of look around and we're like, they just do. Why would that make them nervous? Because why should the universe be that way? Why should the mathematics that govern these fundamental principles of how the universe works be so simple and so elegant and so beautiful? Mathematicians, of course, who are Christian, look at that and say, well, duh. We know, because the God who runs the universe, if you look at this God who incarnated himself in Jesus Christ, this is the kind of God that we see in Jesus, a God who loves beauty, a God who likes to see things restored to order, a God who likes to take chaos and make simple processes out of it. So of course, God would sustain the universe in these very simple ways. Now, sometimes you'll hear people talk about these as the laws of nature, or the equations that govern the laws of nature. I will admit that I fell into that trap until I was straightened out by a Christian mathematician and physicist who said that is a secular trap that the world is trying to suck us into. Because if you think about it, what do we believe from our first articles of our creeds about how God interacts with the universe and regular everyday processes? Who gives us house and home, land and animals, spouse and children, food and clothing? God. We don't want to fall into Newton's trap of saying, oh, yeah, God set the conditions way back at the beginning for that to all happen, but now it just happens automatically through laws of nature. So God's not really very busy. He's like, I've instituted E equals mc squared. I don't have to worry about energy being converted into matter anymore. The better way to think about the laws, equations that govern these interactions of gravity, interactions of mass and energy, is that these are the ways that God ordinarily operates the universe. We are actually watching God at work. This is how God does things. And God is a God of order and not of chaos. And so it's of course natural that we would find equations that are showing us how God does these things, and that they're orderly, and that they tend to repeat themselves. Now, under Newton's scheme, we had a problem of miracles. If you look at the New Testament, of course, people will point and say it's impossible for dead people to rise from the dead. It's impossible for sick people to be healed instantaneously. It's impossible for water to be turned into wine. Why? And often an appeal will be made to things like Newton's laws. We know the laws that govern everything, and they are regular and they are inviolate. They always work this way. Starting with relativity, Newton or Einstein starts to put chinks in this view of the universe as always working in this clockwork fashion. And in fact, it turns out that the universe is a little bit more complicated than we thought. And the reason we are able to find that out is because we're able to examine things that are bigger and take longer and are further out in space than we were able to before. As long as we're just working with our little teeny tiny anthill of humanity, Newton's laws work. It's when we start to expand our vision that things get more complicated. So one of Newton's fundamental discoveries is that time is actually relative to your frame of reference. Time is not an absolute. You can't say 1 second here is the same as 1 second over there, is the same as 1 second 100 years ago, the same as 1 second 100 years in the future, without putting constraints on what you're saying. So mass and size and the speed of light and time are all relative to each other. They're all not that they're relative to each other, they are related to each other by that fundamental equation, which, if you look at it, might seem very complicated to you, but it is in fact, again, pretty elegant. It's not a very complicated equation. Anybody with some very, very basic arithmetic could figure out the missing values. If you know the mass of something, and you know a time in a certain frame of reference, and you know the speed of light, which is constant in a vacuum, then you can figure out the rest of the equation, the rest of the unknowns. What does this mean? Well, for those of you not familiar with relativity, many of you probably are, but just a quick refresher. Here is an implication of general relativity. Let's suppose that the Canadian Space Agency actually builds a spaceship, like an actual one, and we don't just pay somebody else to build the spaceship and operate it for us so that we can put astronauts into space. And Parliament passes a law and says we're going to build a spaceship, and we've got enough funding to get that spaceship to our closest star. Not the sun, for those of you who are geeks, and the sun's the closest star. It's like, yes, the next closest star, which is, anybody know? Betelgeuse is actually pretty far. Alpha Centauri, or its neighbor Alpha Proxima, is a tertiary system, right? So Alpha Proxima, which is what, 4.5 light years away from Earth, which means that light traveling in a vacuum will take 4.5 years to journey from the Earth to Alpha Proxima. Or, I should say, it takes 9 years to make the round trip from the Earth to Alpha Proxima and back. That's very important, going to come up this afternoon in a later presentation. Why it's a round trip and not a one-way trip. So Bob on the left is the lucky astronaut that we put into the spaceship. Fred is the member of Parliament for Kitchener-Waterloo, who is the minister responsible for science and technology. So his job is to keep getting re-elected so that he can keep the funding going for the rocket ship program. So Bob goes up and we accelerate his spaceship relatively close to the speed of light. Let's say 50–60% of the speed of light, which, by the way, is no small feat. That takes an awful lot of energy to do that. But let's suppose we do it, and the spaceship gets out there, and Fred keeps getting elected. He has now served in Parliament for, let's say, 3 parliaments. And Bob comes back and lands on Earth. Even though they were twins, when Bob went into space and went off on his journey, by the time Bob gets back, he will actually be quite a bit younger than Fred. Because Bob has been traveling closer to the speed of light, time in his spaceship relative to time on Earth has slowed down. So he will actually age slower than Fred, who is back here. That's a little bit weird. But it is in fact the implication of relativity. If we were able to get Bob very close to the speed of light, let's say 99% of the speed of light, it is possible that he could make that round trip, and only a month or 2 has passed for him in the spaceship while 9 years has passed on Earth. Which means that in some sense he has done what? Traveled into the future. Which has implications for time travel. Now, you might be saying, well, is this like real? I mean, or is this just a theory? Well, the reality is, any of you who have used one of these and the map feature on your smartphone to get around have made use of the theory of relativity, because we take relativity into account in the GPS system. Because it is in fact the case that our satellites, because they're moving incredibly fast, have a little bit of time dilation effect on them. Time operates a little bit slower for them than it does on Earth, and if we don't compensate for that, you will end up driving to Sudbury instead of to Ottawa. And while I love Sudbury because my grandparents were from there and I spent a number of years there, Ottawa is my hometown and I'd much rather end up there. So, the other implication, of course, of relativity is that not only does time change, but so does mass. This is one of the reasons why, as you get closer to the speed of light, it takes more and more energy to keep accelerating your spaceship, because the mass of your spaceship actually increases. Time slows down, your spaceship gets more massive, and so do you, and your spaceship decreases in length. It actually shrinks. I'm going to let that sink in for those of you not familiar with general relativity. So, as Tony Campolo once put it in a discussion that I heard him give, if you are struggling with a weight issue, you can just tell somebody, I'm not overweight, I'm just traveling too fast. And once I slow down, I'll lose some mass. So technically, if you were to accelerate that spaceship to the speed of light itself, the mass of your spaceship would be infinite, and it would take an infinite amount of energy to keep your spaceship going. That's why it's very difficult to accelerate something close to the speed of light, because mass, length, time are all relative, hence the phrase relativity. What that also means is that the way you view things and measure things like mass and time are relative on your frame of reference. Where are you in the universe? Are you watching the spaceship come towards you? Are you watching the spaceship recede from you? All of those things have to work out so that the speed of light never changes. So for example, we're used to the idea that if you're on a train and the train's moving at 100 kilometers an hour and you're standing on the train and you start walking towards the front of the train at, say, 5 kilometers an hour, what is your absolute speed relative to the ground? 100 plus 5, so it's 105 kilometers an hour. You are going 105 kilometers an hour, but it doesn't feel like that because you're on a train that's going 100 kilometers an hour. But somebody from the outside watching you go by sees you moving at 105 kilometers an hour and the train at 100. What if the train is going very close to the speed of light and you're walking on it? You can't be walking such that you're going faster than the speed of light. That's why the mass has to change, the length has to change, and the time has to change based on your frame of reference, so that you can't be walking faster than the speed of light towards the front of the spaceship. Because the mass, the length, the time, all of that adjusts to keep the speed of light inviolate at 186,000 miles per second. This is the point where I at least stop for the first time, it won't be the last time, and say, this should introduce you to the idea that the universe, already with this very basic concept that now has been around for 100 years and that we apply actually in a lot of different areas of technology, is kind of weird. So when people come to me and say, Pastor, I don't believe the Bible because it has weird stuff in it, it's like, then you haven't studied physics enough. Because the universe is weird. A lot weirder than Newton thought it was. You are probably still operating in a Newtonian frame of reference, or you would give the Bible more credibility. Try that phrase, your friends. You need to move into an Einsteinian frame of reference to better appreciate what God is trying to reveal through His Word. Okay, now if you think general relativity is weird, we're now going to shrink scale. Okay, so we've now looked at the big universe and discovered that once you get to big things moving very fast, time gets very weird, mass gets weird, length gets weird. We discovered that when you went the other way and got down to very, very small things, the same thing happened, and in some ways, things got weirder. For a long time, again, operating in a Newtonian frame of reference, we simply assumed that the universe is kind of like a Lego world. And we're made up out of little tiny Lego bricks. We don't know how small they were, but we know that they're small. And so once you get down to the smallest Lego bricks that make up the pews, stained glass windows, the church building, your own bodies, they will operate on the same Newtonian laws that we do and our cars do and our trains do. That was the assumption. So people kept looking for the smaller and smaller and smaller Lego block. We called them by a Greek word, atom, right? We're looking for the atoms and what happens in an atom. Well, around the same time Einstein's working on the big stuff, people like Max Planck were working on the really small stuff and discovering that atoms are a whole lot more complicated than we thought. And in fact, the rules that apply to big objects like us do not apply once you get down to very, very small things. So people like Max Planck started to make very crazy statements that sounded very religious. All matter originates and exists only by virtue of a force which brings the particle of an atom to vibration and holds this most minute solar system of the atom together. We must assume behind this force the existence of a conscious and intelligent mind. This mind is the matrix of all matter. I want to start with this quote before I explain quantum mechanics. Because sometimes people are told, especially younger people, if you want to be a scientist, you got to give up religion. The people that laid the foundations for general relativity, Einstein and his successors, and the people that laid the foundations for quantum mechanics had the veil lifted from their eyes because they were Christian. Except for Einstein, but he is a unique kind of category. So Einstein couldn't get to the Christian God, but he at least got to the point of saying, gosh, something's going on here. People like Max Planck said, we're starting to see how it is that God actually holds things together at the most minute level. Now let's talk a little bit about this thing called quantum mechanics, which is the set of theories and models and laws that govern the smallest particles in the universe. The first basic idea is that once you get down to the atomic level, particles act digitally. How many of you are familiar with analog versus digital? Okay, some of you are. Just a quick refresher. Analog's the idea that something continuously flows. So think of a river or a highway, right? The traffic is flowing down the highway. I was a traffic engineer originally, and we would do computer modeling. And the original traffic computer models from 30 years ago modeled traffic as if it was water down a pipe. It was not super accurate, but it was the best that we had because our computers were very slow. When you think digitally, you think on and off. Yes and no. Exists, doesn't exist. And there isn't necessarily a flow between the ones and zeros. Okay? So when I mean particles act digitally, it means that particles appear in one location or in another location without necessarily a path of transit from one place to the other. So if you imagine the Conestoga Highway, but you imagine no roads between the exits. So your car is at the exit, and then it's at the next exit, and then snap of the fingers, it's at the next exit, and snap of the fingers, it's at the next exit, instantaneously passing from one to the other. Now at our level, the level of regular human life with cars, we don't see that happening, right? If I had an apple and I wanted to roll it across the piano, I wouldn't push it here and then you would see it instantaneously appear over here. You would see it go through a succession of points across the piano. But once you get small enough to the atomic particle level, electrons, neutrons, protons, things start to jump. And we call the space of that jump a quantum, the smallest space. So when you say something is a quantum leap, you're actually saying it's an incredibly small jump. But we use that to say it's a big jump because we mean it passes from one point to the other without any visible way of getting from one to the other. So it's we say it's a quantum leap because we mean we don't see a path to get from A to B, and yet somehow it's happening. That's why we call this quantum mechanics. Now, the second basic idea of quantum mechanics is, because remember, we're looking for that smallest Lego block, is that we discovered that there's no block. Everything sort of disappears at the subatomic level the way we think of things existing. So the block is both a block and a wave. And we can't really tell which it is until we look at it. There's an experiment that you can do that in fact proves this. And it's called the double slit experiment. And it's where the first concepts of this idea of quantum mechanics started to arise. If we take a board and we put two slits in the board and we shine light on this board, light acts like a wave. So if this were water, you could do this if you've got a lake. You could make a little pond and you put a barrier in the lake and you put two little holes for the water, or slits for the water to go through, and you drop a pebble. The waves from that pebble are going to hit those two holes in the barrier, and they're going to start interfering with each other on the other side. Crests and troughs of waves in the water. And if you put another barrier down here, you're going to find some places it hits as a wave, some places it hits as a trough. Waves, troughs, all across that board, and it will sort of peter out as you get further and further away from the two slots. If this is what you do with light, you just take this board with the two slots and then you put a barrier on the back and you shine light at it, you get an interference pattern on the back wall, which would suggest that light is acting like a wave in water. But what exactly is the light? Right? We're curious people. We want to know, well, what is it? What is happening in between here? Because we know what water is. It's made out of H2O molecules, and we can look at those. But we're trying to figure out what the light actually is. So what would you do as a scientist? Try and see what's happening over here. So if you put a guy with a microphone or a magnifying glass here to see what's going on, the interference pattern disappears. And the light starts acting like it's a particle. And you get a particle. If a particle goes through here, it has to hit here, right? And a particle goes through here, it has to hit here. Take the guy away, interference pattern again. Put the guy in to observe it, you lose the interference pattern. Which would seem to suggest that our observing of what the light is doing is changing the way it behaves. How is that possible? In a Newtonian world, it's not. It just doesn't make sense. Isaac Newton would have looked at that and said, But the quantum mechanics physicists had to figure this out and give an explanation for why this is happening. And the explanation is, we don't know. But it works. There are laws that govern subatomic particles, and all of those laws work. We can use them to build laser pointers, and to build computers, and to build cell phones. And so general relativity powers the GPS locator on the phone that quantum mechanics has allowed us to build. All of the math works. And yet, General relativity and quantum mechanics, the sets of equations that govern them, are incompatible with each other. They cannot both be right. But they both work. But they can't both be right because they don't reconcile with each other. This is why you will hear physicists talking about the search for a theory of everything. How do we get these two theories, one that governs how very, very small things work, and one that governs how very big and fast-moving things work, to work together? Because right now, they don't, even though they do. But they don't. So all sorts of crazy ideas have been proposed, and we'll talk about some in the next hour, to reconcile these two ideas. This was Stephen Hawking's life work, to try and find a way to reconcile them. One of the biggest discrepancies between the two is on something that is so basic and fundamental to our everyday lives: gravity. What is gravity? General relativity says that gravity is a warping of space-time caused by a massive body. So, warping of space-time, sounding a little bit Star Trek-y, which is why I gave the title I did to Pastor Hart about Musings of an Engineer-Scifi-Pastor, because it does sound this way. You have to imagine for a minute, a two-dimensional world. Imagine a sheet. So for those of you who change your beds every now and then, take a bed sheet and stretch it out. You need two people. Now imagine a rubber ball that one of your children comes and throws into the middle of that sheet. What's going to happen to the middle of that sheet? It's going to sink down. Less around the edges, more as you get closer and closer to the ball. Now, if you were to very carefully take a little light ball, maybe a marble, and set it so that it's spinning inside that sheet, it'll tend to spin closer and closer into that indentation made by that ball. It will go into orbit around that ball until the orbit decays because of the friction with the sheet and gets closer and closer and closer and falls into that rubber ball. Okay, do you got that picture in your mind? Okay, here's the tricky bit. Now you have to imagine that our 3 dimensions of space and 1 time dimension, because we really have a 4-dimensional space-time, exist in a 5th dimension into which the 3rd dimensions and time are being curved. So the Earth makes a dent in a 4th dimension into space, which causes the moon to do like that little marble and run around and around the Earth, and causes the sun to make a giant indentation in 4-dimensional space, which causes the planets to roll around the sun. That is general relativity's explanation for gravity. It is not quantum mechanics' explanation for gravity. Quantum mechanics says gravity is a particle, from which we get Star Trek and their wonderful anti-graviton fields, right? We're going to put out a graviton beam. What the heck is a graviton? No one's ever seen one. But quantum mechanics says there has to be a particle called a graviton that conveys gravitational force between bodies. Which means, in theory, you could have an anti-graviton that could cancel out the gravitons, and you could make an anti-gravity car that could go flying around the streets of Kitchener, as if you don't have enough accidents already. Have you ever thought about flying cars? I mean, seriously. Have you seen the 401? We're driving in like 1 dimension, forward and backward, and look how many crashes we have. Can you imagine if we're all flying through Toronto? There'll be cars dropping out of the air all over the place, GO trains smashing into GO buses. I didn't want to think about that. So somebody promises in the election flying cars, do not vote for them. So, quantum theory, gravity, all of this stuff, quantum smears, things jumping from one place to the other, observers affecting whether something's behaving like a wave or a particle. What that's made is a theory, quantum theory, that says that really a lot of things in the world that we thought were impossible are actually just improbable. Quantum theory is based on another idea, third last idea, and that is the idea of uncertainty. I can know where my wave particle is, but I can't know how fast it's going. Or I can know how fast it's going, but I can't know where it is. I can know a little bit of its speed and a little bit of its position, but not both of all of them. What that means is that at a quantum level, at the smallest Lego block level of reality, everything is sort of a smear of probabilities that build up to our level, to my body always staying in one place. It doesn't have an arm over there and a leg over there. But probabilistically speaking, that could happen. I could wake up one morning with my arm over in another bed. But it's highly improbable that that would happen. Like 99.99999999999% chance of my body remaining intact. What is the difference between saying something is impossible and saying something is improbable? Well, if it's impossible, it can't happen. If it's improbable, it could happen. If one has the right conditions, if one has the right power, if one has the right know-how, if you give it enough time, if you get lucky enough. What does that do to the concept of miracles? One of the reasons we can't walk on water, for example, is the way that liquid water molecules line up. Once those liquid water molecules, if they were to miraculously all line up in a certain direction, quantum field theory would say, well, then it would be able to support weight. But that's highly improbable that they would ever line up all exactly at the right time and the right place so that you could actually bear weight on top of that column of water. Highly improbable. Which means we've gone from a Newtonian world where we'd have to say it's impossible for somebody to walk on water to a world under quantum mechanics that says it's only highly improbable. This is one of the things that I would have you think about. I think sometimes Christians are very quick to talk about something being a violation of the laws of nature, being supernatural, God suspending the way He ordinarily works. Instead of, I think, the more we know about science, the more we should simply be saying, God is doing something that we do not have a handle on yet. Is He necessarily, quote unquote, violating the laws of nature? At this point, I'm not sure we have a pretty good grasp on what exactly the laws of nature are. Under Newton, we thought we had a pretty good idea of what was possible and impossible. Under relativity and quantum mechanics, we're not entirely sure on what's probable and improbable anymore. So I have found a lot slower to say a miracle is something that is a violation of the laws of nature, something that is supernatural, instead of saying what we are seeing is the God who runs the universe directing our attention towards something by doing something absolutely out of the normal order of probability. Let me give you an example. Let's suppose you've got a loonie. And if you flip a loonie, you can either get what? Heads or tails. What is the chance, flipping the loonie once, of getting heads? 50-50. If you flip it a second time, what's the chance on that second flip of getting heads? Still 50-50. Third time, still 50-50. Now, what is the probability of getting heads, heads, heads? Yes, that starts getting more improbable. Let's suppose you flipped the loonie 100 times and got heads every time. Would that draw your attention? Would you examine the coin closely to see if it's well weighted or balanced or if there's been any fiddling with it? Probably. If you determine that the loonie is totally normal and the flips have been totally normal and nonetheless you've got heads 100 times, what are you left with? Something really weird, right? But have you violated the laws of mathematics and probability? No. In the same way, if you read John's Gospel, when Jesus does what we call a miracle, what does John call them? A sign. And what does a sign do? Grabs your attention. It pulls you out of the ordinary course of life and says, hello, watch this. Pay attention. Something is going on here. And then it points you in a certain direction. In the same way, if Jesus had had a coin, and had flipped the coin 1,000 times and got heads every time, and everybody examined the coin and said it's totally normal, no violation of the laws of probability except to say that it is incredibly improbable that that should happen, but it would get your attention, wouldn't it? In the same way, Arthur C. Clarke, one of my favorite science fiction authors, even though he was an atheist, said, any sufficiently advanced technology will always appear to a lesser civilization as what? Magic. Why would we be marveling at the idea that when God does something that are way out on the tails of probability or way out in the realms of science that we have not even uncovered yet, it would look like magic to us? What it is a sign. Because every time God does a miracle, it's not just to say, hey, look at me, I'm God, isn't this cool? It's always to do what, Lutherans? Direct you to your salvation. It always serves a salvific purpose. It's not just God doing a cool thing for the sake of doing something fun. Every miracle in the Bible, ask your pastor, traces back to a salvific act of God. I am the God who saves you, who redeems you, who delivers you from sin and gives you life. Every time. All right, how much time do we have? Do I have time for one more topic before our break?
20 minutes.
Oh yeah, lots. Now we're going to shift into mathematics. Pure mathematics, and we're going to tie mathematics to consciousness. Because while the physical world and the world of technology and internets and electric cars and automatic driving systems and all of that has captured everybody's attention, and everyone's like, ooh, you know, how does that reconcile with faith? And hopefully you've seen that actually quite well, and it's doing a much better job at pointing us to the true nature of God than Newton did. Mathematics does the same thing in the other realm that really bothers people, which is, why am I a human? What does it mean to be a human being? What does it mean to be conscious and aware? You know that people are trying to develop artificial intelligence. I'm going to give you an atheist who was a professor of Stephen Hawking's, who has basically said artificial intelligence is impossible on the route that we're going right now. And he's going to explain why using only mathematics. And the cool thing about this is it involves a whole bunch of Lutherans. First, guy up on the upper left, George Cantor. His dad was Jewish, converted to Lutheranism. George actually wrote some really great letters back to his dad talking about his faith and his theology. Letters written at his confirmation about what that meant to him to confirm his faith publicly as a Lutheran. Very troubled individual. For some reason, Lutheranism seems to attract depressed people. I don't know why. We know about that from Luther and C.F.W. Walther and Francis Pieper and George Cantor. However, brilliant mathematician. Really, really brilliant. And his mathematics dealt with the concept of infinity. What do you guys know about infinity? Like really big, right? Cantor asked a question that nobody had really thought to ask. Are there different sizes of infinities? How is that even possible? Well, that was Cantor's initial question. Is it possible that there are different infinite sets of different sizes? Kind of like Goldilocks, right? It's like a big infinity, a medium-sized infinity, and a small infinity. And which infinity do you want to use? So here's how he started his thinking. All right, let's think about whole numbers. Whole numbers, for those of you not familiar, are like 1, 2, 3, 4, 5, 6, 7, right? You can have a set of all the whole numbers. Is the size of that set the same as the set of all even whole numbers? 2, 4, 6, 8, 10. Is that the same size infinity? I want you to think about that for a minute. All the even numbers and all the whole numbers, same size or not? How many of you think same size? How many of you say different size? How many of you got that from reason? How many of you got that from empiricism? How many of you got that from intuition in your gut, right? Well, I'm going to give you the revelation answer, although I'll try and do a little bit of the logic behind it. They are actually the same size. And his logic went like this. Let's suppose you have one pie on one side and you have 2 candies over here. I can match up one pie with 2 candies, another pie with another 2 candies, another pie with another 2 candies, and go on so on to infinity. And each has a match, and therefore it's the same size infinity. Then he went and said, a bunch of other sets, but this was an interesting one. What about the set of all whole numbers and the set of all real numbers? All right, now I'm getting you back into your high school mathematics. What is a real number? Real number is 1 to 2 and all the numbers in between. 1.1, 1.11, 1.112, 1.113, 1.1131, etc., right? So you got 1 to 2 and all the numbers in between, and then you've got 1, 2, 3, 4, 5 whole numbers. Are those the same size infinity? No. Because for every pie over here, I can get another candy over here that doesn't have a pie over on this side. That was his logic. And he worked this all out mathematically and set up a proof for this and said the set of all real numbers is a larger size infinity than the set of all whole numbers. At this point, Catholic mathematicians started to get angry and upset and wrote letters. So we've got to shut this guy down. Why would they care? Why did religion or theology get involved in this concept of set theory and the size of infinities? How many of you are familiar with a man named Thomas Aquinas? Okay, Thomas Aquinas was a Roman Catholic theologian in the 12th century who is famous for devising 5 proofs for the existence of God. Or evidences, right? Chains of logical reasoning. One of them was God is the largest set that you can imagine, right? He is the infinite. If you can imagine an infinite, well then that's God, because infinity is the most you can possibly have, and since God is the biggest possible being, then he is coterminous with that infinity. If you have a guy come along, and a Lutheran at that, who says, but there's different size infinities, then which infinity is God? Now, Cantor didn't care, because for Cantor, the proof for the existence of God is where? In Scripture. It's in the Word of God. It's God's revelation of himself. It's not from our reasoning. I cannot by my own reason or strength believe in Jesus Christ my Lord or come to him. So we have always been suspect of people like Aquinas and their logical proofs for the existence of God. But here's Cantor coming along and saying infinity here, infinity there, big infinity, small infinity, and then he asks the question that Goldilocks would naturally ask: if there's a big infinity and a small infinity, is there a medium-sized infinity that would be just right? And so he started looking for this proof, and he proved that there was. There was an infinity that falls in between this size of the infinite set of real numbers and the infinite set of whole numbers. But Cantor, being a Lutheran, wasn't satisfied. You know, we can never just rest. We've got to like always be poking at our holes at our own ideas. So he's like, is it also true that there isn't a medium-sized infinite set? And he proved that too. He proved two contradictory things, that there is a medium-sized infinity and there is not a medium-sized infinity, and try as he might and try as other mathematicians might, they could not find a fault in either mathematical proof. This is a problem because it means you are proving two contradictory things. Quantum mechanics is bad enough. Is it a wave? Is it a particle? Depends whether you're watching it, etc., etc. We didn't even talk about Schrodinger's cat. That's where Schrodinger's cat and the box and all that comes into that. You guys familiar with Schrodinger's cat? Well, because you can't know whether something is a wave or a particle or where its position is, Schrodinger, who was a quantum physicist, came up with this thought experiment. It says, what if you took a cat and you put it in a box that was closed and you had an atom that was either going to decay and become the next isotope or not? Well, until you observe it, you can't know which it's done, so it's done both decay and not decay, which means that the cat is both alive and dead, because the atom would decay and trigger a poison vial. Right? That's the idea. So the cat is both alive and dead until you open the box to see which it is. From a quantum point of view, this actually is the case. You would not know whether the cat is alive or dead. It's in a state of quantum superposition is what we call it. It's both alive and dead at the same time. Quantum mechanics, it's weird, but we live with it. So in the same way, we now have infinities that exist and don't exist. Well, what do we do with that? Well, everybody sort of, as we like to say in our day and age, put a pin in it. So we're going to leave that aside for now. By the way, for a long time, people just didn't want to fool with Cantor's set theory at all. They just said, this is too crazy. After a couple decades, people said, it's crazy, but it's incredibly useful and powerful mathematics. So if you go up to the Faculty of Mathematics with your pink tie on, the University of Waterloo, and you talk about George Cantor and set theory, everyone will nod, they'll know what you're talking about. This is all perfectly accepted mathematics. Kurt Gödel, also a Lutheran, colleague of Einstein's in Princeton, picked up where Cantor left off and said, what are we going to do with this idea that you have a theory that is both proved and not proved? He says, we got to do something with it. And so he looked at it and looked at all the work that had been done and said, I can make a theory out of this fact that you cannot prove whether there's a medium-sized or not medium-sized infinity. And his theory came to be called the incompleteness theorem. And it is also a fundamental axiom of mathematical set theory. What Gödel proved is that within any mathematical system, there will always be things you have to take on faith that cannot be proved. No mathematical system can be completely internally proved. There will be certain things that you're just going to have to say, I'm just going to believe this so that I can get to work and do the math. Now think about that for a moment. This is an amazing thing because we like to think of mathematics as being all about reason, all about logic, all being provable and well established. And yet Gödel comes along and says, even in math, we have to start from certain things where we're just going to say, I'm going to take it on faith because it works. Even though I can't see it and I can't logically prove it. That leads us to Roger Penrose. How many of you have seen the movie A Theory of Everything? Okay, so Roger Penrose has a prominent role in that movie, right? He is the mathematician that David Thewlis's character, who is Hawking's supervisor, took Stephen Hawking to go and see in London, to take him to that seminar. And Penrose ended up being on his doctoral thesis, a supervisory committee, and they did a lot of work together. Penrose knew all about Gödel and knew all about Cantor. And in his later years said, we need to think about what this says about intelligence and consciousness. That we as human beings are able to prove something that within a mathematical system cannot be proved. Why is that important? Because of these. Your cell phone, my cell phone, is basically a computer that is way more powerful than the thing that sat on my desk at Conroe Gable College 24 years ago. My godparents in Grand Bend, my uncle is a GP, doctor in Grand Bend, Lambton Shores, offered to buy me a computer because I was starting to study engineering. And they bought me a 386, if you remember those, 40 megabyte hard drive, a megabyte of RAM. It was state of the art. My roommate, who was a computer engineering student, only had a 20 megabyte 286. And everybody was in awe. And I had, get this, kids, a color monitor. Everybody else, it was black and green. Black and green was all you had. I had a full color screen. We could play Tetris, man. It was so cool. And back then, do you remember when you had Tetris and you could hit the escape key and a fake spreadsheet would come up so it could look like you were at work? Oh, those were the days. So anyway, I had my 386, but that 386 had a fraction of the power that this phone has right now. Now, artificial intelligence and the search for AI is based on the idea that all our brain is a super powerful organic version of this. And once these get to be as computationally powerful as our brains, they will naturally become conscious and will all become batteries in a giant computer-run world living a simulated existence a la Matrix, right? Penrose said, because he's British, poppycock. Why? Because our phones, our computers can only operate on the principles of mathematics. They cannot make leaps of faith. They cannot believe something contradictory. A computer cannot figure out Gödel's incompleteness theorem. But we have. And we know that it's true, even though it states that it is impossible within any mathematical system to prove everything. So Penrose has kind of made a name for himself, writing a series of books where he's used Gödel's theorem and Cantor's theorem to demonstrate that consciousness has got to be something more than sheer computing power, because our brain is able to do what a computer cannot do, which is determine Gödel's incompleteness theorem and evaluate it and use it mathematically. And he's demonstrated that a computer can't do it. Computer can't use set theory. Only a human brain can. Now, Penrose has an explanation for this. He thinks it has something to do with quantum theory because he's big into quantum theory. He thinks there's something that happens in our synapses in our brain that causes them to operate at a quantum level. And as we know in quantum mechanics, impossibilities become improbabilities. Observation plays a role in whether something happens or doesn't happen. And so he thinks something fundamental is happening at that level. We, though, as Christians, can say whether that explanation works or not, we have known all along that we are far more than simply powerful organic computers. We're created in the image of God. And God is consciousness and awareness. And we have a small part of that because of the image that we've been created in. And here is science and mathematics saying, yeah, you're right. We don't know how, but somehow something happens in the brain that makes it more than just a computer. Your soul, your spirit, some connection with some entity that exists in a parallel dimension like Scientology. We don't know. But we do know that it is there because Scripture says so. How much time do we have? Yeah, so here's what I'm going to do. I'm going to say when we come back, we are going to start talking about the elephant in the room. The thing that really, when we talk about why is there a debate between science and religion, everybody immediately jumps into, oh, evolution, oh, Big Bang Theory, oh, age of the universe. I don't like to get into that until way later because I think some of this other stuff is far more fascinating and far more useful. Because it's when we get into those theories that we really start to get into the question of how do you know that? And we start to leave mathematics and physics and good operational science behind and start to get into the realm of time travel and history and things that ultimately are not going to lead us to more powerful computers, better vaccines, and longer lifespans. But really start to get into the realm of philosophy and where do you think the universe comes from, less than how do we know that this is where the universe comes from. So we will break for lunch and we will talk more about that when we come back.